Hey guys, welcome back. This is going to be, let's see, what is this, Wednesday? So only day 2 so far. Seems like it's still pretty early. Only day 2 of the week for IC&D 2. It's thrown me off because we didn't start on Monday. I looked at the slides today. I was like, man, we should be further along than we are. But we're actually doing, we're doing all right. We're at a pretty good place. Before we started, I just kind of checked the pulse. I wanted to make sure everybody was doing okay so far. And one of the things that was requested was a little bit more, just a refresher on spanning tree, which we actually have more spanning tree ahead of us in the slideshow. So that was a pretty good request. I couldn't ask for anything better than that as feedback. But as we continue through our journey, at any time, if you feel a little bit disoriented or you feel like overwhelmed, like you just kind of spaced out for a moment, and you're like, how did this work? Just ask. You could say quick recap question mark in the room chat, and I'd be happy to give you just kind of like a maybe 15-20 second recap of how that protocol or technology works. Just if you need it from the high level, kind of top down again, let me know. So anyhow, without any further ado, let's jump back into right where we left off yesterday, which was looking at spanning tree. And I said by default on Cisco Catalyst switches, not all Cisco switches, but Catalyst switches. This is what you typically find in a LAN environment. The other type of switches that exist are Nexus or MDS. These are out there. You may pass them in your server room. The MDS is a storage-only switch. It's for SAN, and the Nexus combines the SAN capabilities and LAN capabilities into one switch. The Nexus operating system is actually built on the old SAN OS. So there are other Cisco switches out there that you may encounter. They run a different operating system. Nexus actually runs something called NXOS, and it has slightly different commands and slightly different defaults. But when we look at our Catalyst switches, these would be like 2950s, 2960s, 3560s, 3750s, 45 and 6500s, and so forth. Those are all classified as Catalyst, and you'll find that they're going to run per VLAN spanning tree. It's going to be enabled on all ports by default, and this has got slower convergence than rapid spanning tree protocol. This is that 802.1W. So just quick recap of what we talked about yesterday. Spanning trees are a loop prevention mechanism. If we get a loop at layer 2, it's going to mess up the way that we learn which MAC addresses live on which ports. If you screw that up, the whole network is shot. The layer 3 protocols are going to time out. You're going to have tons of packet loss. You're going to have poor voice over IP, poor quality in your voice over IP. You're going to have angry users. So we need to make sure that this doesn't happen. As you can see here, Cisco runs spanning tree by default. So in Cisco environments, it typically doesn't melt down. When you start to get outside of the Cisco realm, you find vendors that don't run it by default, and you get yourself in some pretty interesting situations. I've seen entire companies the network literally dies. Everything goes to 100%. They've got to shut it all off. They've got to pull out network cables. They've got to reprogram it from the ground up. I've got a good friend who's got a business that actually happened. They used a different vendor because it was a little bit cheaper. They had somebody come in and install it, which was fine, but then they bought some other switches on their own and thought they were okay adding other switches to the environment, which at first they were, until one of the employees was leaving. It was her last day at work. And she just tidied up all the wires at her office and wound up taking 2 ports in the wall. There's a lot of wires back there, and she had disconnected all the cables. She went from one port in the wall to another, created a loop between 2 switches, brought down the entire company on a Friday afternoon. And it was a printing company, and they had a lot of jobs that had to go out. About a 100-person company, and the entire company came to a screeching halt. The salespeople couldn't make phone calls. The guys that were the graphic artists creating the print jobs, they couldn't submit the print jobs to the press. Everything was basically frozen. And we had to go through and then shut off all the equipment. They turned it all back on, and it worked for a little bit, but because that loop was still there, it came tumbling back down again. So if you know what you're doing and you turn on spanning tree on those other devices, you're going to be fine. But the idea of not running spanning tree, in my opinion, is completely suicidal, because as soon as one person, if you can guarantee me that no one is ever going to mistakenly plug a wire into the wrong place, you'll always be fine. But should anybody create a loop with a wire, and that's what I see as redundant topology. I was told, and I was always brought up that you should never have a single point of failure. So in those scenarios, if you are going to have two types of connectivity and you're going to have an alternate path, you need a protocol that can compensate for that. And that's where spanning tree really comes in. It's important that we run it, and it's important that we kind of appreciate the significance of what it does for us. So just a recap of where we are with spanning tree and what Cisco does by default. So looking at per VLAN spanning tree plus, this is technically what Cisco's doing. Per VLAN spanning tree. Now this is confusing because they'll tell you that you do PVST, but when you do show commands, it says IEEE, which is talking about the 802.1d standard. This was the original spanning tree by Radia Perlman. So for example, if I come over to my demo box, let's jump over there for a second. Valentina says, should I enable spanning tree on all interfaces? It's on by default if it's Cisco. If it is not a Cisco device, you need to check with the documentation. I think some of the other vendors are kind of hurting themselves by not turning it on because the customer is most likely going to have a bad experience. I would say turn it on, and then if they want to shut it off, by all means, let them do that. But you definitely want it on unless you've got a really good reason not to. So looking at our 3750 here, if I were to do show spanning tree, this is where the confusion comes in. It tells you spanning tree enabled protocol IEEE. Well, when we talked about it, we said there's a standard 802.1d that's defined by the IEEE. Well, that's what you're using by default, it would seem, right? But this is under the context of VLAN 1. And if you go down to the next VLAN, VLAN 40, once again it says IEEE. And then once again under VLAN 127, it says IEEE. So this was confusing as all get out for me because I was like, wait, I thought we're doing PVST. Why does it say IEEE there, which was the original? Well, what's going on there is that within VLAN 1, you're running 802.1d, which is the original spanning tree. Inside of VLAN 2, you're running 802.1d. So what does that really mean? Well, this is a trunk link. Agreed? Does everybody remember trunks from yesterday? And a trunk link is going to have what VLAN as the native by default? Which VLAN is going to be the native VLAN if I don't change anything? VLAN 1. Which when it says PVST or per VLAN spanning tree, think about it literally as stp.exe. This isn't the name of the process, but if this were a Windows box, you'd see stp.exe running, and you'd see it multiple times. Like if I launched 10 instances of calc.exe, you'd see them all running there. So spanning tree protocol sends something called a bridge protocol data unit, BPDUs. He sends these every 2 seconds. So when this process sends out a BPDU, it goes out on this wire with no tag. Does that make sense? Because VLAN 1 is native by default. What's going on over there on switch 2 is that within VLAN 2, he's got stp.exe running. And technically they all do. But I'm just showing you from the perspective of the root bridge. So he's sending out a BPDU, but it's going to be tagged for VLAN 2. I'll just put V2 there. And if I was to create VLAN 5 over here, as soon as I create VLAN 5, there's a new spanning tree.exe. It's not really .exe, but there's a new spanning tree process that's once again sending out BPDUs every 2 seconds. But they're going to be tagged with VLAN 5. Does that make sense? So if I had 25 VLANs and I were to sniff this wire and nothing was going on, I would at a minimum see every 2 seconds a burst of 25 BPDUs. Do you guys follow that? Because every single VLAN has a spanning tree process running. And every single VLAN, if you wanted to, could be engineered a little bit differently. You could have 25 different root bridges if you wanted to. Normally it wouldn't make much sense, but that's the, I guess you could say that's the flexibility of per VLAN spanning tree. You can run a different logical topology with different forwarding and blocked ports for every single VLAN. Why would you want to do all that? Well, let's just kind of go back, and we talked about this yesterday, but let's revisit it. If there was only a single spanning tree for the entire environment, well, let's say it was this, the one with root for VLAN 1. This would be our root bridge, which means this is in the forwarding state, and this is in the blocking state. The downside is that 0% of our traffic is ever going to cross that link. And that makes me sad because these are 10 gigabit per second uplinks. So what per VLAN spanning tree aims to do is perform some load balancing. It's not really load balancing though. It's load sharing, and here's why. By setting up different switches to be routes for different VLANs, you get a different spanning tree topology. So if you look at what's happening for VLAN 2's traffic, VLAN 2 says, I'm going to forward on this link, I'm going to forward on that link, but I would block over here. Does that make sense? So having multiple spanning tree instances allows us to utilize our uplinks more effectively. I can distribute some of my load. So now that alternate path that was a 10 gigabit per second lane is no longer 0% of our traffic. Now maybe it's broken up with 45% of our traffic here, and then 55% of our traffic on the other link, but this is only traffic coming from VLAN 1. Does that make sense? Let me see some thumbs up if you guys are with me, and if you're not so sure, tell me what's confusing you. We've got to have a loop-free mechanism. That's what spanning tree is. The idea that we're doing it multiple times is so that we can always forward on all of our links. It'll never be a true 50-50 load distribution. Traffic just doesn't work like that. It's never that easy. But if you see 70-30, you can go, all right, cool. Because one of my links would have been totally pegged. And right now, I've got a little bit of it going each way. So just gives us the ability to use multiple uplinks. Use them more effectively. All right, so that's PVST+. What's going on behind the scenes of PVST+ can be pretty confusing though. How many of you remember me telling you the default system priority? I said when we do an election for the root bridge, the device with the lowest priority is going to win. So this is the first thing that we look at. The bridge ID consists of the priority and the MAC address. Does anybody remember what the default priority is? And I hope all of you do. Mentioned it a couple times yesterday. Eric, good job. 32.768. So I would take things like this, like I would learn them in class or I would read it within the book and I'd go, okay, mentally, 32.768, remember that, and you'd go through and you answer right on the test and you get your merit badge and they go, congrats, you're a CCNA. And then you go out in the field and you never really see 32.768. So I was like, it always confused me. Like I learned certain things, but then it didn't really add up. Kind of like that IEEE. Well, this is what's going on with your priority. Yes, the priority is 32.768, but what Cisco does with PVST is they extend this with what they call the extended system ID. So they say your priority is 32.768, but we modify it by adding a system ID extension of 127. Where the heck does 127 come from? 32.768 is right. Yeah, you're close. And Mark, you said priority 0. That's what we put on the root bridge. So your head's still in the right game. And Chris, correct, that is the VLAN ID. So what's going on with Cisco, you go, wait a minute, I thought we're doing PVST, but it says IEEE. Well, it's doing the original spanning tree inside of each VLAN. That's how Cisco customized it. It allows us to build different logical topologies for each of our VLANs. You can go crazy with this and implement some really cool traffic engineering. Well, additionally, what they do is they come in and they modify that 32768 by adding your VLAN ID. So here we are with 32895. If you follow what I said, and I know Todd does because he says, is it the VLAN? Yep, that's your VLAN ID. What would be the priority on VLAN 1? One more time, we say in Cisco the default priority is 32768, but you never see it because they modify it. You never really see 32768. It's like 32768 or whatever priority you set it to plus the VLAN. So what I was after there, and Eric nailed it, 32769. They say take the priority, and in this case I have priority 0. But if I didn't, you'd have a system extension ID of 1, which would set that to 32769. Let's see if this one has that. Show spanning tree. There we go. So here we see bridge ID. This is us. The root defines whoever the root is. The bridge is who we are. So when you say show spanning tree, and it does it on a VLAN by VLAN basis, it first tells you who the root bridge is, and then it gives you information about yourself. And sometimes under root ID, it'll say this bridge is root. So for example, if I come over here and I look at VLAN 40, it only exists on this switch. So what's our priority? Well, I just set it to something wacky. Here's the MAC address. These two together form your bridge ID. And it tells us right here, who's the root? We are. So if you look below, like I could take that priority and address and compare it to this and figure out that I am in fact the root, but it's easier that they tell us. So coming back over here, just looking at VLAN 1, we see that our switch has a priority of 32769. And again, all I was clarifying that in the book or in the slides, they'll tell you the default priority is 32768. That's before they add the VLAN extension. So again, like if you come down here and you look at 40, they'll take this priority and they'll add 40 to it. And there's what you actually see in your output. Is that making sense? When I took my CCNA, they just kind of banged across this, and I had things that confused me for quite a while afterwards. Can't answer all the questions. You'll still probably have some, but just trying to get the obvious stuff out of the output so you feel more comfortable. Cool. So the system ID is derived from your VLAN, and what they do is they take the priority plus the system ID and add it together, and that's how we saw 32769 on VLAN 1. Groovy. So modifying the bridge ID, we can say show spanning tree VLAN 1, and here we see our priority and our MAC address. These two values combined form the bridge ID. So if I want to change the bridge ID, what we typically do is lower that priority to make sure that that switch will become the root bridge. So what I can do, there's a couple ways to do this. I can say spanning tree VLAN 1 root primary. This is what I call a macro command because it forms kind of an indirect function. What spanning tree VLAN 1 root primary does is it says, look at what's going on with spanning tree. Look at who the current root bridge is. And you know what? I want to be the root bridge. So lower this priority enough to make me the root. That's what that command does. I could say spanning tree VLAN 1. Let me just show you. I could come in here and let's take a look at our VLANs. So VLAN 777, for example. This is one that we built yesterday for a demonstration. And let's say that I wanted to modify that. I could say conf t, and I could say spanning tree VLAN 777. And if you question mark, you can see here I could say root primary, and that's what I describe as a macro because it's going to look at other BPDUs in your environment and it's going to say, what do I need to do to win? And it's going to lower your priority, not all the way to 0, but just to be one step below your neighbors so that this device wins. So this is kind of an easy way to do it. Another way that's a little bit more manual is I can say spanning tree VLAN 777, and I could say priority, and then we specify a number. Well, your bridge priority is supposed to be in increments of 4096. And I believe if I just put the number 5, it'll multiply it. Nope, it didn't like it. But it did give me a legend that says use 0, 4096, 8192, etc. So I could say 0, 1, 2, 3, 4, 5, and I could make my priority this. So spanning tree VLAN 777 priority, and I'll just paste that in. Now when I say show spanning tree, I can scroll down to 777, and we should see that new priority being set. So it was 20,480 plus my VLAN ID, which gives me this. Are we feeling pretty good on priority? And the reason that we would lower that is because I want a particular device to become the root bridge. Cool. So moral of the story, just as a quick recap, there's 2 different ways to do it. I could hard code it, and it showed me you could add up, in 4096 times X, and I could say this is where I want it to be. Or alternatively, I could just say make me the root. There's a root primary and a root secondary command. That's what we typically stagger back and forth on our 2 root bridges. So in your environment, you might have core 1 and core 2. These are the main switches in the center of your network that other switches connect to. And maybe your network's not that fancy. But we go to one of these, and I say, you are going to be root primary, and you're going to be root secondary. So what may happen is this guy, the root primary, will drop it by 2 parameters. What are those 2 parameters? Let's go back here and look. Where's my cheat sheet? 32,768 was the default, so I might set the first one to 24,576 and the second one to 28,672. That's what that would do for us. In other words, this becomes 24576, which means he's the root, and then this is going to be 28672, which means he would lose the root election unless this is offline. If it is offline, this guy wins over anyone else that has 32,768. Does that make sense? We just want to make sure, should anything fail, that core 2 becomes the center of the network and not some access layer device. So Todd says, I might be off track, but if you had 3 switches, one was a 2900, 2960, 3750, the 2900 would be the root. You might not want that, so you could manually do the root command. Absolutely. Yeah, what could happen is that a device that's a little bit older, and where are the older devices in your network? Is it in your data center with, dual air conditioners and power supplies and power conditioners? If you live in a crazy lightning-filled area like Tampa, we've got all this stuff, cabinets and RFID badges and security cameras on our server room or on our data center, and then those have wires that run around the rest of the campus. So if you look at an old crummy switch, the oldest switch in your environment, is it in your data center or is it somewhere else? I don't know. I'm asking you guys. You got to tell me. Where's the oldest, crummiest switch in your company? Maybe it's under your desk. Todd says not in the data center. Eric says at the access layer. And then what happens is if some old crummy device over here, here's this 3500 XL switch. This thing was built in the 90s. It's fast Ethernet only, but it absolutely will not die, right? And you guys, that's what I'm talking about. In the storage rack, at the loading dock, in a maybe in a test environment, maybe, just probably in the least important part of the network. And then what happens is if everybody's got the default priority, he becomes root. And then when you look at the 2 next switches up, they wouldn't send traffic over this path, but they'd send it over this one. And these could be fast Ethernet ports where this was gig Ethernet. But it doesn't matter because this is the root bridge. And then up here on your core switches, that's kind of like that customer I told you about yesterday. That could be 10 gig, but if this is the root, that 10 gig path is going to be blocked. That's going to be blocked, and these are going to forward. So if there's ever traffic going from core 1 to core 2, it's going to go from that 3500 XL to get there, which is not ideal, but it is also not a loop. So it's suboptimal, but it still works. That's the cool thing about spanning tree. A lot of people complain about it, but having it is way worse than not having it. And it's just a matter of kind of tweaking it the way that you want to get things to perform the way that they should. All right, so looking at the spanning tree topology, if you want to analyze it, we can start off by doing show CDP neighbors. What is this going to do? Well, it's going to show us who's connected. And as we saw earlier, I've got Dell and HP devices on my network that are speaking CDP to me, which is completely crazy. Now, this is a Cisco class, so as far as we're concerned, everything in your environment Cisco and CDP rules the world. But if you were in a mixed vendor environment, and there was maybe some Juniper out there, and there was some Arista out there, and maybe some Ruckus for your Wi-Fis, what might I use to see all these other devices? Yeah, maybe some Brocade. Is there another protocol that competes with CDP that might give me some visibility? Cisco doesn't focus on this a lot, but I found it to be really useful in customer environments. LLDP, Link Layer Discovery Protocol. This is something that ideally everything's going to run. If I had my way, this would run on printers, this would run on IP cameras, you name it. Just everything announces everything all the time. You log into a device, you can see exactly what's on each of your device, what's on every single port. Is it a camera? Is it a printer? Is it an Xbox? Is it a Wii U? Like that type of information should be broadcasted through LDP. It was a 12-year window between when CDP was released and when LLDP came out as a standard. 12 years, which is like 100 years, because they talk about dog years. It's like 100 years in computer years. It was around forever. So it's finally here. It's a standard. Anybody can implement it. Servers are starting to. You're starting to see support for LDP in some of your operating systems. But ideally, we'll get to a point where every device can do LDP. You might think that's terrible. You might think it's a big security risk. But I'd at least like it to be an option so that if I'm in an environment where it's appropriate, I'd like to turn it on. Additionally, we can use our spanning tree knowledge to kind of, and this is what I recommended that you do, look at your topology in Visio. And if you don't have a network diagram, let's get that fixed. Go ahead and start making one now, even if it's Microsoft Paint. That's better than the one you had before because there was none. Ideally, PowerPoint or Visio, let's make it a little bit prettier. Let's get all of our data in there. Look at your environment and go, okay, based on what I know about spanning tree, where is forwarding occurring and where is blocking occurring? And just go back and kind of, you could sketch it out pretty easy and then go look at your environment and you can try to figure out why is it working the way that it's working? Why is it forwarding? Why is that particular switch the root bridge? If you didn't touch anything, chances are there's no load sharing and there's suboptimal traffic. If you did configure it correctly, you should have load sharing. You should have two switches. This one says he's the root for some VLANs. This one's the root for others. So if you look at a switch, if the switch has two uplinks, he's sending some packets on one and some packets on the other. Probably never get a perfect 50-50 split, but you will get some load sharing there. All right, so we can look at the path and make sure that it matches what's expected. And maybe you don't know what to expect. Maybe somebody that worked there before you built it all and you're learning this for the first time and you hope it's right. Well, it probably isn't. If it is, kudos to you. That's great. You got lucky. But if it isn't, that's cool. It gives you a chance to go in there and make the network better without buying anything. That's always my favorite thing. If I can go to a customer site and say, we can make your network work much better, and you just have to pay for my time. I'm not trying to sell you a new product or a new load balancer or some new firewall, some new acronym, some license. I just need to configure it properly. Remember that VLANs have their own spanning tree processes in Cisco. So we can look at this on a VLAN by VLAN basis, and we can verify who the root bridge is. So to analyze the topology, you'd look at your switches and you try to figure out which of these switches is going to be the root bridge. Once we know who the root bridge is, you would expect that ports like this are in the forwarding state. They're going to have the shortest path to get to the root. And then the alternate paths are going to be in the blocking state on the far end. So it looks like that. Technically for switch A, this port's in the forwarding state. But if I look at switch A's MAC address table, and I want to, see what's associated with port 1/17 over here, what am I going to be learning there? Nothing, because the downstream device, this is a point-to-point link. The only thing over there is another switch, and I'm not learning anything on that path. I'm not getting, unicast or multicast or broadcast frames from end users because that port is in the blocking state. So while it says F there for forwarding, the upstream switch could forward things out, and he is actually forwarding BPDUs from the root bridge, which is how this guy knows that there is still a loop. And that's why it's in the blocking state. But that switch isn't learning things in his MAC address table on port 117, so user data is not going to go there. Just diagnostic data, things like CDP, things like spanning tree, LLDP, and so forth. Everybody okay with that? I know it might look a little funny, and if you miss that, you're like, wait, I was reading Reddit, I was looking at ESPN. Was that important? Yes, it's important. What may confuse you, it confused me. I said, why is that side forwarding and this side blocking? Doesn't, switch A know that there's a loop? It's okay because the root bridge is sending out BPDUs. When we get them, we forward them. And that's how these guys, switches C and D, know that there's still a loop. They continue to see BPDUs every 2 seconds, so they know that there's still a loop that way. If something happens and there's no longer a loop, we could transition to a forwarding state. All right. So looking at your spanning tree topology, we've done this a few times. We can say show spanning tree, and if you do that without specifying anything else, it's going to show our spanning tree on a VLAN by VLAN basis. This is VLAN 1, VLAN 2, VLAN 3, and it goes through all of your VLANs. Within the VLAN, it shows us the VLAN number, and it shows us our protocol. That could be the rapid spanning tree protocol. It could be 802.1w if you're using rapid PVST, but iOS doesn't run that by default. NXOS does. Below, we see things like the cost. What happens every time you send out BPDUs is that the cost is going to be calculated. This is how we can find the best path to the root. Cost is calculated based on the speed of the link. If it's a slow link, it has a high cost. If it's a fast link, it will have a low cost. This is cumulative. So as BPDUs go out from the root bridge, as they go out, the cost is going to go up, and these are switches on a hop-by-hop basis. Does that make sense? So by the time the BPDU gets to you, you can look at it and determine which path is best to utilize to get to the root. This is how the downstream devices figure out which of the two paths to use. They're going to choose the path with the lowest cost. The hello time, 2 seconds. This is how often hellos are sent out. The max age is 20 seconds. In other words, if I don't hear any BPDUs on this alternate path for 20 seconds, I'm going to assume that there's no longer a loop. So if that broke, there's no loop. So I can now listen, and if there's no more hellos in those 20 seconds, I can transition to the forwarding state to make that part of the network reachable. Does that make sense? Awesome. Appreciate the feedback. I just want to make sure I don't lose anybody. Additionally, beneath it, we get to see what's going on with spanning tree on an interface by interface basis. I can see who's a designated port. That means this could potentially go out to a downstream device. A root port is what I call an upstream device. That's taking me towards the root bridge. Your ports will be root ports or designated ports. So spanning tree failure consequences. If spanning tree fails, As a process, it fails catastrophically. It is not going to be subtle. Your entire network will be down. So we could have loops, we could have MAC address table instability. It's not going to be good. So in this scenario, they say on switch D, the spanning tree process just crashed. Now, I've seen a lot of weird things. I've seen a lot of weird things because I'm in education, and I get students like you in class that say, I had this happen in my environment, and I get to see weird things because of that. I also get to see weird things because I do vulnerability research on network hardware. So I try to find ways to hack switches and routers and firewalls just as a hobby, because I like security stuff. So I've broken switches a lot of different ways, and I've broken firewalls a lot of different ways. I have not seen, in my almost 20 years of doing this, spanning tree break. Not from me creating bogus packets, not from me doing any strange injections. I've been able to manipulate it, doing things that I shouldn't with Yersinia, but I've never seen spanning tree just completely fail. Not knocking the scenario, just trying to put it into perspective. All right, so before we get into this, Reggie says root ports don't necessarily connect directly to a loop. They're just the ports that you take to the root. Correct, absolutely. You may not have a loop. Like for me, do I have a loop in my environment? Well, let's see. If I go to my 3750, I can say show spanning tree. My main VLAN is 127. And how do we tell if I have a loop in my environment? You could look at this output and you could tell me whether or not I have a loop. Not in all scenarios, because there's more to, you could be doing blocking on another switch, but I don't. There's no blocked ports. Exactly. This is the last switch in the lineup. There's a firewall, there's a switch, another switch, and then my switch. And there are 2 ports that go to the upstream device. This is an important concept. I'm glad you brought this up, Reggie. So I've got my ASA, and it's downstairs, and it goes into a switch. The ASA, you can do something called redundant interfaces on, or you can set up an LACP port group. So if you've got extra interfaces on your firewall, you can bundle them together and treat the 2 physical interfaces as one logical. So I do that to my first switch, which is in the server room downstairs, which comes upstairs, and it goes to a Comware switch, which is HP Enterprise, which comes to my 3750X, which is what I run everything I care about on. This guy's just intermediate. He's got treadmills and Rokus and access points plugged into him. This is where all the magic happens on my 3750. And I wanted to have 2 lines run. I had to run wires through my house to make all this work. And if one of these wires gets severed, my class isn't going to work. So I want physical redundancy. I guess these switches aren't as redundant as they should be, but at least my wires are. So I've got 2 wires. This goes to port 23 and port 24. Why don't I have a loop? Shouldn't one of these be in the blocking state? And here's another scenario. What if I had 4 wires run? Perfect, Reggie. It's logically one interface. I'm using port channels. If you know what a port channel is, great. If you don't, we're going to learn about it this week. You can probably guess. You have a logical interface called port channel 1 that has physical members. 23 and 24 are the physical members of the logical interface. So if you've ever done NIC teaming on a server, it's the same thing. He's using these interfaces as a port channel or ether channel. So with and without spanning tree. With spanning tree and no ether channel, what would happen with 4 links? 3 would be blocked, 1 would be forwarding. Does that make sense? because he goes, look at all these loops. Spanning tree is going to block all those extra paths. So what we do here, and I appreciate the thumbs up, what we do here is we put those into a port channel. So he goes, okay, ports 21 and 22 are part of that same channel too. And when packets come in, or we should say frames because it's happening at layer 2, when frames come in, he's got an algorithm that he runs to distribute load. Some packets go there, some go there, some go there, some go here. So he's doing load distribution, load sharing across all those physical paths. So if you look at what I've got going on, my port 23 and port 24 are part of port channel 1. Those two ports are both in the forwarding state. They're root ports. They're taking me towards the root bridge. Does that make sense? And don't worry too much about these priorities. This is used for now. Just understand this is used for tie breaking when we've got multiple paths. We can look at the priority of our neighbor, and we can look at the interface number. All right. Like I said, I've got one of the classes I've taught talks about nothing but spanning tree for 5 full days. So there is a bit more to this, but we're getting the basics out now. So what will happen if switch D erroneously transitions both of its ports to the forwarding state? In other words, I personally haven't seen spanning tree break, but it's not impossible. Okay? It's a computer, right? These are just applications. If STP-EXE completely craps out and there's not some monitoring process that sees it and restarts it, well, both of these ports could go into the forwarding state. If that happens, you have a loop, and anytime there's a broadcast, things are going to get really weird, because broadcast says send it out every port except for the one that it came in on. This is that scenario where A sends a broadcast, and I go, oh, A lives on this link, and I flood it this way. But a moment later, I see a message from A to broadcast come in over here, and I go, crap, A is on that link. Second later, it comes over here. So my MAC address table is unstable. I keep seeing MAC addresses shift back and forth between the ports. This is what happens when you get that loop. So the consequences of spanning tree failure are going to be severe. Have I seen spanning tree as a process fail? No. Have I seen other vendors get implemented without spanning tree and cause a network to melt down? Absolutely. I'm a certified instructor for more than just Cisco. So on those other companies, when I teach classes, I don't really teach them anymore, but when I used to, the lab problems, 19 times out of 20 were all based on spanning tree. It didn't matter whether it was a BGP class, a security class, a data center class. Some student would erase their configuration on the switch, reload the switch, and boom, everything would go down because there was no spanning tree. So before I reboot this switch, it was so crazy, you had to physically shut any interfaces that went to that switch. If you missed 2 on each switch, you had a loop and your entire environment was hosed. You couldn't even talk to these devices. We had a terminal server, which has got, it's basically kind of like a router that you log into that has console access to each device. When the CPU is highly loaded, this switch becomes unreachable, even through the console port. You can start to type commands, and a lot of times it'll just hang there. So I've seen environments where the console will take commands, but I've seen environments as well where it won't. When that loop is happening, you could have a server here, and that server is maybe dual-homed. Maybe this is for out-of-band access, and this is connected to the internet. Well, because the out-of-band side is getting hammered with the broadcast storm, the internet interface will actually stop replying. Does that make sense? So the connected devices get overwhelmed. I can't even reach that web page. I can't even get to that email server because this other NIC is in an environment that has a broadcast storm. So broadcast storm is something that I heard about literally like in the 90s during an MCSE boot camp to become an MCSE and NT4. Back in those days in Network Essentials, they explained the concept of a broadcast storm. I knew it was bad, never saw one in production because I ran Cisco hardware. Went on to CCNA, heard about broadcast storms, thought they were old, never saw one in production. Got my CCNP, understood it as a concept, never saw it in production. Started dealing with customers that had non-Cisco hardware. Then here was this legendary broadcast storm I heard of for the last 15 years happening left and right with massive outages, all because spanning tree was off. So sorry if I'm beating a dead horse here, but we want to have spanning tree enabled, makes our life a lot easier, protects us from any type of failure. Other things that we can do to make life a little bit more bearable are port fast and BPDU guard. Using IEEE spanning tree, which is what's on Catalyst switches by default, spanning tree is running on every port, which means if you build a brand new server or desktop, let's say you build a brand new desktop for yourself. Here's my brand new shiny workstation that don't actually look like this anymore, but you get the idea. I put in SSD hard drives and I put 2 of them just so that I could get RAID 0. This is blazing fast. System boots in about 7 seconds. I'm so proud of myself. 7 seconds, it's downloading all the device drivers, it's sitting at a desktop, and I open my web browser. What happens when I open my web browser? By default, in 7 seconds. If you don't know, here comes a spoiler, nothing. I have no network connectivity for up to 50 seconds because spanning tree is transitioning through different states. It starts off in a blocking state, then a learning, then a listening, and then finally a forwarding. It takes somewhere between 30 to 50 seconds before this port's going to come up. I just got my brand new system. I'm super stoked about it, but now, here there's like angry bloodshot eyes. I'm completely upset because this system does not do what it's supposed to. What good is it if it boots in 7 seconds if I'm sitting there waiting for 50 for my port to go active so that I can get an IP address so that I can finally get to the internet? See the situation I'm in? So spanning tree is good, but it takes a while to transition to the forwarding state. So what I can do on access ports that are going to my end users is turn on port fast. This says when this port goes live, transition to the forwarding state immediately. And you go, wait a minute, isn't that dangerous? What happens if that user puts a switch in their office and then they create a loop on that switch? Well, we can back up port fast with BPDU guard. Port fast is what we do as administrators to make the users happy. It transitions their port into a forwarding state immediately. The downside is it leaves us vulnerable. If that user takes some crummy switch, I'm not going to say a name of any vendors, use your imagination, some goofy Soho switch that they had at home or got at a garage sale or a flea market, they bring it into the office, they plug it into their outlet, and then they create a loop in their environment, it could affect you. So what we want to make sure is that there's not any switches out there. If I send out a BPDU and it comes back to me, I know that there's a loop. So what we can do is implement a feature called BPDU guard. We implement this kind of like as a sister capability to port fast. Port fast has transitioned to the forwarding state immediately. However, back it up with BPDU guard. BPDU guard says if you ever receive a BPDU on this interface, kill the interface, shut it down. You could shut it down forever, or you could just shut it down for maybe 5 minutes. It's up to you on how, trying to think of a politically correct term to how oppressive you want to be on your minions that are using your network there, these guests of your domain. So what happens if somebody plugs in a switch that doesn't belong? Do we shut them down forever so they have to open a network ticket and then we come and investigate and read the errors and we can kind of shame them? Or do we just shut it off for 5 minutes? Protecting us, allowing them time to recable, reboot, and all of a sudden it automatically starts working. So that's up to you. Just depends on your corporate security policy. But BPDU guard protects us. We say if a BPDU is received, shut down the port. Port fast says transition to the forwarding state immediately. So just for example, we could pop in conft interface gig 1/0/15. You know what? Let's default it. So remember that Control A gets you to the beginning of the line. So I can say default interface gig 10/15. And then on the interface itself, I can enable port fast and BPDU guard. So to do that, those are features of spanning tree. So we go into the interface 1/0/15, and I say spanning tree port fast. It's going to allow it to transition to the forwarding state immediately. Says it's only going to work when we're in a non-trunking mode, which is OK. This is a warning, not an error. And look at what it's telling us. It said port fast should only be enabled on ports connected to a single host. If you put a hub, concentrator, switch, bridge, or anything else that you want to call that does MAC forwarding, it could create a loop and it could take down your network. So it's cool that you use this, but be careful. Instead of being careful, I want to be thorough. So I'm going to say spanning tree. And if we question mark, you see if you've got some other capabilities. I can say, let's use BPDU guard. BPDU guard enable. Now, I'm sure some of you are like, wait, there's other fun stuff there. There are other things that you can tune, and that's why there's a 5-day class on spanning tree. Some of the popular ones are BPDU filter as well. This just says don't send and receive BPDUs on this interface. This can be handy as well. I told you that there's a cost. You can manually manipulate the cost. We can set up different mechanisms for guarding. So you can do something called root guarding. We can stack our switches. So you can enable this as a stack port. You can implement multi-instance spanning tree. So lots of tweaks that we can do on spanning tree. But we don't want to get too far off topic. So how are we feeling so far? We're almost an hour into class. Why would you ever disable port guard, your BPDU guard? Well, it's disabled by default, so that's a pretty good reason. Because it's like that out of the box. But if you enable port fast, you normally want to have this on as well. I would say it's just being thorough. I can't think of an example where I wouldn't want that on if it's going out to an access port. Cool. So these are the commands to enable it. Now, do you want to do it on every single interface? Maybe, maybe not. You could do it as a global parameter. I could say spanning tree port fast, BPDU guard default, and then spanning tree port fast default. This will turn it on all interfaces automatically. And then you could disable it on an interface by interface basis if you wanted. So when you do a show running config, you'd notice that port fast and BPDU guard are enabled side by side. And that's going to wrap up our first section. So in summary, port fast can be used on ports connected to a single workstation, allowing them to boot and get network access immediately. When you enable port fast on a port connected to another switch, you risk creating a loop. BPDU guard says if I ever see a BPDU come in this interface, I'm going to shut this interface down. All right, so that wraps up our first section. Let's go ahead and take our break here. I hope everybody's feeling pretty comfortable with spanning tree. If you feel like you have more questions than answers, that's okay. It means you've got a good mind. When you get to the switch class in CCNP, they spend a lot more time on spanning tree. That's a huge, I'd say almost somewhere between 20% and a quarter of the class is just looking at spanning tree in more detail. So you get into MSTP, you get into functions like root guard. So there is more out there. With other vendors, like I said, I taught an entire class of nothing but spanning tree interoperability. What happens when you hook Cisco to HP? And easy answer is it depends, because there's lots of different ways to implement things on both sides. One of the cool things is HP added PVST support to their switches. So my upstream device integrates pretty well because it's doing PVST on it. Additionally, something that simplifies our networks is ether channels. If I've got a bunch of links going to an upstream device, I could bundle those together wherever possible. That's where you get into PAGP or LACP. If you've used those in the past, fantastic. You're in good shape for the next section. If you haven't seen them, that's exciting too, because the things I show you in the next section are going to give you more bandwidth just using unused ports that are available on your switches. So we'll go ahead and take our break now, and when we come back, we'll take a look at port channels. Hope you guys are having a good time, and I'll see you after the break.